Okay, sorry for the delay. Good afternoon, good morning, everybody. My name is Nadia Pinardi. I'm the director of the Decade Collaborative Center for Coastal Resilience, and this is the Coastal Resilience webinar series that is done in collaboration with CMCC, Deltares, and OTCA, the Ocean Teacher Global Academy of UNESCO Intergovernmental Oceanographic Commission. Okay, so today's agenda, we have two very special talks from engineer Achilleas and Professor Achilleas Samaras from Greece. And then we will stop on some questions. We'll take a break and we'll go again to another introduction, shorter introduction. And we'll have engineer and Professor Patricio Winkler from Chile and some more question and answers from him, for him. We're very excited that both very important engineers in coastal protection are with us. So we see, you know, this is part of the Coastal Resilience School, the first school that we have in this topic, on this topic within the UN Ocean Decade. And the course that these webinars are done for is called Sustainable Coastal Growth and Resilience. It is a 10 weeks online course, plus next week an in-person meeting in Bertinoro. So again, we are sponsored by University of Bologna that sponsors the UN Decade Collaborative Center for Coastal Resilience, the Deltares from the Netherlands, and CMCC from Italy. So again, two wonderful speakers today, Achilleas Samaras and Patricio Winkler. And we start with Achilleas Samaras. Achilleas is an associate professor at Democritus University of Thrace in Greece, and is an expert in maritime hydraulics, coastal engineering, hydrodynamics, also in coastal pollution. His research interests include wave dynamics, sediment transport, coastal flooding, and as needed the design of coastal harbor structures for adaptation to climate change. Dr. Samaras is furthermore the coordinating author of the third World Ocean Assessment, which is soon to be published. So it is time, no, maybe I have to also say this, yeah. The question and answer session, your audio and video are deactivated. So we expect you to write your questions in the section. We just want you to know that we record this webinar, and by participating, you consent to the recording. So again, welcome everybody, and here is the time of Professor Dr. Achilleas Samaras. Please, Achilleas.
Thank you. Yeah. Thank you, Professor Pinardi. Let me share my screen. Yeah. It should be okay now, no?
It is.
Yeah, perfect. So thank you for the invitation, for the kind introduction. We've worked in the past, so Okay, I know, and I'm really glad always when with everything that has to do with the University of Bologna. So the talk today will be about coastal resilience and how we can use integrated modeling approaches to towards coastal resilience, and we'll focus on a particular case on what we call Watershed-Coast Systems. So a quite broad topic, but I'll try to be concise and brief about some of the ideas. When I started building this presentation, and the entire presentation will try to answer or revolve around three questions. So how is coastal resilience perceived and studied in a changing climate, especially? What is the role of modeling approaches, integrated approaches towards building resilient systems? And what hinders the transition from scientific expertise to informed decision-making? I'm sure you've heard a lot about coastal resilience and definitions. It's one of the pillars of this talk, let's say. How do we perceive resilience and what are its components? If you asked ChatGPT, I asked with a few iterations to tell me what is coastal resilience, and give me some infographics about it. So it gives a really nice definition and shows some infographics that try to connect several dots and try to give this, maybe the lower left one tries to give this circular arrow idea that hints that coastal resilience is an iterative process. So it's not something that you design and leave it be in a system, in an area, in a city, wherever, but you must improve it continuously and strive to achieve it, to build a resilient system, a resilient coastal system, coastal city, whatever. The second thing is modeling approaches. And we've used, many of us, models in our lives, and many engineers are using them as well, and people that are involved in the decision-making process. The key role is that models can actually give us what perception cannot. So they give us the quantitative approach of our study of a natural system. So that's the good thing. But in order to pass from the description of a natural system to coastal resilience, to building resilient systems, you need to adapt the modeling approaches you have to fit management purposes and engineering purposes. And this connects to informed decision-making. So to pass from the scientific understanding and description of a problem to the decisions that will lead to building a resilient system, this has to take into account other aspects as well. So not only science or natural sciences, but economic, social aspects. So we need to find a way to bridge the gaps between science, society, and governance in order to build a resilient system, whatever this system might be. So if you see these three bullets, these three pillars are connected. So you expect some exchange of information, and they're connected in this circular way. I try to do this. And let's see now an infographic that is more structured that will help us in what follows. So what we are doing really well, and even better the last few years as natural scientists, as engineers, is to understand the problem, conceptualize it, transform it into mathematical equations and in a numerical model, and use this model to run scenarios about the situation of the natural environment, the built environment, and design solutions. What is missing in many ways, or the complaints from both sides might focus on these, is what we call informed decision-making. That this has to do with this bubble we see here that has stakeholders, policy makers, institutions, and everything that will give feedback to the modeling staff. And then this is a necessary step to translate the scientific knowledge into policy and then build a system. So it's not that we can rely solely on the scientific output. We need to find a way to translate it into policy, to see some of the solutions that we propose and that we design, that we suggest realized in the near future in our region, in our area, wherever around the world. And this arrow, as I said before, hints that this is an iterative process. So if we design and actually come to the realization of a resilient system, then if like a natural disaster hits it, we should see the response. We should see if it responded accordingly to according to our predictions, our simulations, and then restructure a bit or tweak our approach and pass through the same filter and again improve the resilience of the system itself. So that's what we need to do and what we should do. So now how can we structure an approach that will fit a quite complex system, let's say? So these, what we call watershed-coast systems, are systems that include the watershed, the coastal area adjacent to its outlet, that are dynamic systems where the delivery from water and sediment from the watershed actually impacts and affects in long term and the short term the coastal environment. In a changing climate that we're seeing extreme conditions evolve around us, the problem in question can be broken down into these four components. So we have the climate change, the dynamics in the two fields, and the integration of the system itself. So this approach suits the modeling approach that I'm going to present as well. So if we want to put it in a simple flow chart, we have to know what is the impact of climate change into the dynamics of these systems, and then find a way to integrate this system and produce tangible results that we will use again to plan its adaptation and mitigation of hazards. The basic limitations that most studies or many studies face, that actually it's a complex scientific problem. It's not that something is resolved totally ever in this complex system. It's first that many works do not integrate it, not study concurrently watershed and coastal dynamics. So they either study watershed dynamics and provide some output that you can use again if you're studying the estuary or the transitional area, or you're studying the coast and you're getting some data from the watershed near the outlet. But this choice hinders from understanding the dynamics of the entire system because changes happen concurrently in both of these fields, and one is affecting the other, especially in the transitional area. And the second is the scales at which many successful implementations have been presented up to now. So there have been approaches and integrated modeling approaches that try to study systems of the entire Earth or large-scale dynamics that actually produce results that can provide us with understanding about, let's say, the evolution of landforms. So the evolution of an estuary in times that are like centuries or millennia, and they're quite reasonable. But the problem is that these results cannot easily be translated into action and design of mitigation and adaptation against climate change, because one, there are really large-scale simulation, both in space and time, and second, it's not easy to present them to a non-specialized audience and get feedback from them or agree or disagree about it. So the current state of the art, focusing on these systems and mainly in the morphodynamics modeling that is a step more advanced than this, more complicated, was described in a recent paper, and that I sent to Annalisa to provide to everybody as a publication that some of the presentation today will be based on. So there have been successful applications of integrated modeling approaches that try to overcome some of the limitations. No approach is perfect up to now, and they're continuously improved, but there have been some really interesting steps. But what are we still missing? What is the missing link or the missing idea in these integrated modeling approaches, especially when it comes to climate change and simulating future climate or future conditions in such systems? a really fundamental flowchart of a modeling approach that will be to study, let's say, the morphodynamics of such systems will involve this. But you can, here we're focusing on morphodynamics. You can also say that you want to focus on water quality or floods. The fundamental approach is the same. So you need to have some models and results that can study the climate, analyze global or regional climate model results, and see how these pressures affect the dynamics in your systems. First, in the watershed, so you need models that can simulate water discharge, erosion, sediment discharge at the outlet, and then you need to see the impact of the climate on the coastal field, the ocean and coastal field. So you need models that can take climatic or weather pressures and translate them into waves, sediment transport, erosion, flooding in the coast. And then you need to find a way to integrate this modeling system. So couple these models, calibrate them, validate them based on the knowledge we have up to now, based on actual field measurements. For example, for erosion, the shoreline position and the bathymetry is a basic indicator. So once you validate your modeling approach, then you can project, implement like different pressures in this system and see what its future behavior should be. So the present and future states of the watershed-coast system are essential to understanding how you can proceed. But one thing that many modeling studies are missing, or we have not found yet a really good way of representing actually with accuracy, is how we model the future conditions in the watershed. What is typically done also from this flowchart, you can understand this, is that we take the validated system that we have now, the validated models, and then apply pressures, future climatic pressures, to see what the response of the system would be. But what this approach is missing is that we're missing all the indirect effects of climate change that have to do not directly with the climatic or weather pressures, but on the changes that will have happened or will happen in the watershed and in the coastal field during this time, up to the worst case or mild case scenario. So a framework will need to be adapted so that we have this gray area, the projected changes in the system, in management practices and in engineering works. For example, if we have climatic pressures increasing in such a system, for example, in the watershed, extreme rainfall or droughts or whatever, changes will happen in the system until the time that the actual pressure will come. So maybe a dam will be constructed, maybe some other river regulation. In the coast, the same. So if we see climate change coming, it's not that the system will remain the same at its validated test case that we build and will not change. We will build coastal protection measures. We will build whatever else. So these direct effects need to be taken into consideration so that afterwards we can see the ecological, the socioeconomic implications and resort to and provide with guidelines for management and engineering purposes. So essential aspects of this approach as we move towards this approach can be broken down into several steps that you can use, of course, as plug and play in many cases, because not every system will be the most complex system possible. Not all systems will have all the interactions and all the natural processes, but you need to identify which are relevant to your case study. So first is the analysis of the system. So you need to have information about geography, about morphology, about historical data, the main pressures, the data availability, the key stakeholders. And thankfully today we have many resources to do so. There are systems like Copernicus, like NOAA, USGS, databases that provide us with satellite information, measurements, modeling results, you name it, about the conditions up to now, but also future projections. But also we need to know other stuff. We need to know what are the main pressures from the human environment. So what are the main activities in the area? How have they evolved in the last 20, 30 years? You have Eurostat, you have the World Bank, you have observatories about the environmental condition and results from projects that give us a lot of information about how several areas around the world have evolved over the past 20, 30 years. We have UNESCO databases that show us where the World Heritage sites are that might need to be protected. We have environmentally sensitive areas that need to be protected. We have the World Bank has a database about the infrastructure and their evolution in different areas of the world. So, and of course, there are local governments and authorities that provide this information. So first of all, you need to analyze at a larger scale your system and see what is relevant in your case. What are the main pressures there? Then you need to go to the climate change and see the results you have and projections you have about the future climate and the future scenarios. We have the IPCC reports and many other organizations like the WMO, Cordex, Copernicus, and ESGF are initiatives, systems, whatever you call them, that provide large-scale global climate model results or downscale the regional climate model results. So all these are input to our models. We have availability of information, but we should focus here on this third bubble that says projected changes in management practices and engineering works. That has to do with what I mentioned before. So we do not only need the change in pressures, but we need the change in the actual condition of our system. Actually, IPCC, if you look at it, in the latest reports, moved beyond the RCPs, the representative concentration pathways that were scenarios about the emissions that you use to build different scenarios about climatic pressures, and they now included these third socioeconomic pathways aspect, leading to these third climate policy assumptions. So these SPAs are scenarios that actually include both the pressures in a broader sense, but also the conditions in different regions of the world about the policy that will be leading to climate change over these next years. And the mitigation and adaptation reports and everything now are based on these SPAs and not solely on the impact on the climate system itself. So this is a really important consideration to take into account. Then we can move to the dynamics of the systems, the models. We have to model watershed dynamics and coastal dynamics in transitional areas. Again, we have modeling approaches. Some are described in this paper and in this work. Some are ongoing, of course. We have a great arsenal of models and modeling system nowadays, from open source, open access, from in-house institutional models that are developed by research centers like the CMCC, for example. Many universities have done their work on this. And you need to, again, not every case, every system will be the most complex system of all. You need to highlight the main drivers in each system based on history and trends, and see where you need focus. Because again, here the bubble that says decision about models appropriate complexity. When you study a phenomenon in a watershed-coast system or wherever, you need to see what's important for you. There are models that study waves, let's say, in scales of seconds, or CFD models that actually try to see real detailed dynamics of, let's say, wave structure interaction. But there are also models that study long-term wave condition trends or ocean circulation. The same in watershed, there are models that will focus on the turbulence and the ripples in a riverbed, but there are also models that can simulate water and sediment discharge across an entire watershed, an entire region. So you need to decide the appropriate complexity, and as it is now, we need to say that the simpler or reduced complexity approaches are the ones that can work better in this concept. So you need to decide what your level of accuracy you want is, and if this level of accuracy can be validated based on measurements on the present conditions, you're okay with a quite certainty to move forward with this approach. Then you have, of course, the design of the mitigation and adaptation options that, of course, based on the previous, will need to be, again, modeled in your approach. So if you build a dam, there's a way that you can introduce this in a watershed scale model. If you build coastal protection or whatever else, you can model this in the coastal, on an integrated coastal protection model that designs structures and can reproduce the interaction with the wave and the morphodynamics. And then you go to the part that we said, the tricky part, the society and governance part, in a way that you can actually see your idea or your proposal or your concept being realized. In Europe, we have the EU adaptation strategy that hints where the situation is going. So you cannot be in a European country and not take into account where the European policy is going, because to put it simply, your project, your approach, whatever, will not be funded in any scenario. So again, we have knowledge from the assessment of planning of different projects through the EEIs and SEIs that you see here that provide information not only on the actual modeling part, but also about the assessment, the interaction with stakeholders, the planning. And you need to have some basic understanding on how natural, along with social and economic scientists, approach the overcoming adaptation barriers when we have to do with stakeholders and with policy and with policymakers. So this is a lot to deal with, but not one person will do everything. So yeah, and then you need to have some economic tools that actually will bring your solutions and assess them, evaluate them, and produce a scenario that will lead you to coastal resilience, to building a resilient system. This is maybe a lot to grasp, but I'll try to just pinpoint some key considerations. So for a scientist, an engineer that is trying to deal with this informed decision-making aspect beyond the mere scientific understanding, you need to avoid presenting hard to relate or hard to grasp aspects when communicating with policymakers and the public. The first one means that there are so vague the results that you show that no one can relate to, because they do not relate to their actual problems in real life. And the second has to do with hard to grasp. If you're being too technical, you get into really details about all the processes. These are really, really complicated subjects, even for scientists to communicate effectively. So some basic points is, first, we need to rely to approaches with real life applicability if we want to see coastal resilience approaches being realized in the field as a management, as structures, and as infrastructure, as everything. This goes beyond the, as I said, the scientific understanding of processes, but we need to adapt our approaches so that we can see projects and approaches being realized, being built, being adapted by regions, by countries, by whoever is involved. Then we need to understand that these problems have to be, in many cases, case-specific. So you cannot study generally the situation of the coast in Greece and come to specific projects, because the stakeholders that will be involved will have competing interests or different interests in many cases. So an area might have agricultural production in the watershed and tourism, another might not. So you need to focus on your system, because an integrated modeling system can better describe it and produce with tangible results about it. Third, you need to rely on sound quantitative results. So you need to focus on a few fundamental indicators. For example, for erosion can be soil imposition or the flooding extent, whatever. But this is a really basic and easy to grasp indicator, and you can use this indicator to communicate what will happen to the system, to assess the costs, the benefits, the impacts of the proposed solution, but also run do-nothing scenarios. So if you go to stakeholders or policymakers, you need to have an arsenal, scientific arsenal, to say, okay, this is what we've done up to now. You see that as things are going, this is the projected situation of this system. And you will have this impact on the loss of land. You will have this loss in economic activity, these projected changes in agriculture or in the land cover. All these aspects need to be quite clear and quantified, and you need to have scenarios, because future states, as I mentioned, need to be based on scenarios. We're not gods to predict accurately the future, and you need to compare with a do-nothing scenario. So if you do these steps, this will cost you this, but the alternative is this. And this is what the final decision and policy should and hopefully will be based. So we must learn, and it's hard for many natural scientists and engineers to bring on board expertise from economic and social science that will help us not refine our models, but build better scenarios about what the future will be. So the future scenarios we said about the system should be based on some fundamental social and economical aspects of how the system, the human nature system will respond to climate change. And we're seeing it evolving these days. And of course, we need to keep in mind that scales are of essence. Large-scale phenomena or large-scale models cannot describe accurately situations or conditions in narrow field, the ones that can easily relate with the local policymakers. Probably, of course, for a country, you need to have some wider picture. You need to have some integrated picture of the entire evolution. But if you want to successfully base your assessment on quantitative results, you have to go to scales that will be case-specific. And I'm going to close with a small example that shows what we're discussing up to now, what I've tried to present up to now. So let's say we have a hypothetical case study about such a system in the Mediterranean. So we've done our work, we've identified the system, we said, oh, what do we have here? So in the watershed, we have agricultural activity, and the main stakeholders are people that work in this sector, and the economic activity is based on this. In the coastal field, we have a small coastal city that is related on this, is dependent on tourism, but we also have an archaeological site that needs to be protected, and a coastal and protected ecosystem that we do not want to lose. So if we get the data we have up to now from all the databases, and we structure the present climate, so this blue scenario that we see here, based on this and the measurements we have up to now, we can see and evaluate and calculate and validate our models, our modeling approach, and say, yeah, we have not observed significant changes, so I've validated my model, it's okay to go. I need to now test future scenarios. If we study the projections about the changing climate, let's say we narrow down two scenarios. The yellow one, that is a milder change scenario, and the red one. What I've discussed before is that the easy thing to do, and what many studies up to now were doing, is implementing these climatic pressures on the system that has, the modeling system that has been built up to now. But in under a changing climate, the watershed will have changed when the 2060 scenario comes. The coast will have changed. So the correct thing to do, even modeling-wise, to get the results we want to get about the adaptation and the building a resilient system, we'll need to assess what will happen, assess some scenarios about what will happen, and say, okay, for example, with an increase in temperature and reduced rainfall, we'll have some mild hydrological and agricultural drought that will affect cultivation practices, will affect this activity. So land cover or land use will change in the watershed during all these years. And the coast, on the other hand, will change. We won't see higher waves coming, even mildly higher ones, and not create some coastal protection measures to protect the activities, to protect the ecosystem, to protect the archaeological site. So this is the future state of the system that you need to take into account modeling-wise beyond just the climatic pressures. If you go to the extreme scenario, then you'll have, for example, the watershed, you might examine a scenario that you'll have, let's say, extreme drought and fires in the watershed. You might have the construction of a dam that will be used to alleviate the hydrological drought that will affect the crops. So these changes can be modeled and should be taken into account when you try to build this future state of your watershed-coast system. And the same in the coastal field. You might have to resort to hard defense solutions. So coastal protection with hard defense works, as we said, and all the activities will feel the impact until this scenario comes. So the idea from this is that we need to incorporate in a pure scientific natural science idea of modeling the Earth system aspects that will have to do with indirect effects of climate change. So closing, the idea of this presentation was to present this framework that is quite adaptable, but gives you a really good idea about how you can use integrated modeling approaches towards building resilient systems. There were some tools and concepts. Whoever searches the details of the paper can delve into the intricacies about the modeling sources. It's far too complicated to include it in a small webinar, but I hopefully you've gotten a quite clear or somehow clear idea about how we can use advanced models and advanced modeling approaches to bridge these gaps that we said in the beginning. So to bridge the gaps between science, society, and governments. And this is what we need to do if we want to see coastal resilience or resilient system being realized, actually to see them in our area, in our city, in our country, wherever. That's all from me. Thank you. Thank you for your attention.
Thank you very much, Achilleas. Very nice framing of the problem, the complex problem of getting not only the science correct and right, but also the interface with the policymakers. So we have a question here before I ask mine from Kingsley. How do one communicate the hard-to-grasp concepts without leaving out the true state of a problem or its enormity?
Yeah, this is not easy to do, okay, but the solution is to necessarily rely, as I said before, on a few fundamental indicators. So you might not need, and nobody will understand you if you try to explain the entire range of morphodynamics. But if you present even to not specialized audience, for example, the coastal erosion extent you predict, the one that you have validated with your model up to now, and the one you predict, this is an indicator that is easy to grasp. So you understand that erosion is where the shoreline moves inland. Accretion is when it moves towards the sea. And another key is associating these basic fundamental indicators with and translate them in economic and social terms. So if you manage to translate how this loss of land will impact the uses you have in the coastal zone or in the watershed, the economic activity and the social structure of the area, you might get more easily, more welcome, you might find more welcome ears to hear about what you're presenting.
Thank you, Achilleas. We have another question by Ellen. What would you say to countries who approach climate resilience in the coast and catchment separately? So your nice watershed coast continuum, but something that is separate. Yeah.
Yeah, again, when you have, it depends again on the local systems. For example, there are, of course, several coastal stretches that are not connected with a watershed upstream, so you might not need this entire approach. Also, there might be watersheds whose activity, whose areas near the outlet do not host some of the aspects we saw here. So if you do not have some really high importance environmental, world heritage, or social activities near the outlet, you might avoid these. But when you have a watershed, the cost will be affected. Whether you choose to study it because it has activities that impact your system, your region, your city, whatever, this is a valid question. But if you have systems that are connected, the best practice, the best idea is to study them concurrently, even at reduced complexity, because this way you can capture how pressures evolve over time and how the seasonality of pressures affects the systems. For example, compound floods that have been discussed, and it's a hot topic in the last few years. If you focus on transitional areas or only the watershed, only the coast, it's not a given that the higher coastal flood will coincide with the higher flood from the inland. So compound flooding by itself is a phenomenon that also depends on the seasonality. So you need to understand the dynamics of both these two fields to understand their interaction at the transitional area. You cannot do one without the other, or if you do it, it will lose some information that might prove quite useful to you. So depends on the actual system, depends on the actual case you're studying. So if you do not have a river nearby or a watershed that affects, you might not need this integrated approach, but in many cases, especially for morphodynamics, because the main source of sediment are streams and rivers, you need this coupled system to describe dynamics better.
Thank you, Achilleas. I'm a bit more radical than you are, and I would say that this is a silent revolution that has occurred in the past 20 years. Finally, engineering at the coast has been coming closer to oceanography at the coast, but also hydraulics from the land has come close. And we cannot lose, we've gained a lot of expertise now, and now it's possible to get the two together. And the solution is clearly when you look at the two problems together. And there is no doubt now. Clearly, it will be at various degree of amplitude of this coupling. The coupling is not always the same. But definitely, the way to go is stress the system so that you look at the two coupled.
I agree.
Stress the system. So I like your very nice indication on the use of indicators. Too many indications. So usage of indicators is something that would pave the way for more communication to policymaking and we're still kind of preliminary there. That's my impression. But there are other issues that I think I'd like you to ask to comment. And another one is the connection of the watershed and coast with the industrial sector, which is a very important part of our society. We normally interface a lot with sort of the final users, but upstream with us, with the scientists and engineer, there is the industrial sector. And that relationship is still very difficult, in my opinion. Why is it so? And how we can change that in the future?
Yeah, that's even trickier than dealing with policymakers and stakeholders. In many cases, this has to do because still there's no good communication, and these sort of approaches that try to integrate a lot of aspects are seen as something or not relevant for some people, or maybe that could harm their industry or their approach. Because once we establish these connections and we establish systems that are working in an integrated way, you will also have like attribution of fault or of merit when where you need to do it. So if you model an integrated system like this, a watershed-coast system, you will be able to monitor, let's say, changes in the watershed, in the water quality, dredging, aspects like this that cannot be explained by the measurements, cannot be explained by the model. So that's also a typical problem in many modeling approaches, that you take all the data, you describe the best you can the natural problem, and you see that you're missing something. We were doing work back then in a small watershed-coast system during my PhD, and the changes in the natural and human environment could not explain what was happening in terms of loss of sediment from the watershed. And the actual investigation resulted that there was some illegal dredging along the riverbed that was to be accounted for the changes. So from a very simple example, you see that if you monitor and model these systems, you will be able eventually to, I don't know, the industry, if they're willing to do so, because of course there's industries that are willing to contribute to this, but also to, as policy, as stakeholders, find the sources of many environmental or social by expansion problems. So this is not a battle. This is an ongoing stress that will happen as we're getting better into modeling these systems and getting results that are actually tangible. Because also from the industrial sector, a main shortcoming of science basis up to now is that, oh, these you're saying are too probabilistic, not realistic, whatever. But if you find a way to translate the changes into actual easy to grasp concepts and show the impacts in terms of social and economic impact, then people will be moved, either the industry wants it or not. It's a bit radical, but it has to be this way.
Yeah. So we have Bernard has a question. Do you have an idea how politicians and leaders can be convinced when they pursue short-term goals, economic, for votes and ignore environmental concerns?
Yeah, we need to translate better how the environmental problem also translates in economic terms, economic and social terms. Even when having to convince politicians that think about their elections, if at the policy or at stakeholder level, you show that the way we're going, if we do not adapt or build a resilient system, you will have not just the loss of sediment, not just the loss of biodiversity, not just the loss of whatever flooding area, but you translate it in economic terms and social change terms, so actual impacts of a modeled phenomenon, then it will be easier to do so and harder to rebut, harder to ignore.
Thank you very much, Achilleas. And I think it's time now to take a break. We will take a 20 minutes break. We'll meet again at 15:10 and continue with our next speaker. And we hope you can join us, Achilleas, anyway.
Yeah, of course, I'll be here.
Yes, and we can conclude with a longer discussion. Thank you very much.
Thank you.
See you soon. Okay. Interrompon. Okay. Good afternoon, good morning, everybody. Thank you for remaining with us. Trying to find my presentation here. Let me see. Yeah. Yeah, today's agenda. Now, let's see, I have to share the screen. Just a second. I have to take out this remote control, this one. And now finally, we see the agenda again. So now, I'm very glad to have with us Professor Engineer Patricio Winkler. And here, let me give you a short introduction. Patricio is a civil engineer who has pursued postgraduate studies in many countries in Europe and the United States, and he has also earned his doctorate at Cornell University in 2015, the engineering university in the United States, I have to say. So he's now Ocean Engineering Group. He joined the Ocean Engineering Group at Valparaiso University, beautiful, in Chile. Okay, so his research interests cover engineering, arts, and the philosophy of science. That's very interesting. Thank you for being with us, Patricio. We're all ready to listen and to be inspired.
Thank you, Nadia. Pleasure to meet you today, and also to know that I have a former student who works with you, Rodrigo Campos, Chilean, working his PhD there. So it was nice to know that. And well, so this is a very I need to share the screen, and I have no choice to make it.
So let's
I need
see.
someone to.
Yeah, we are trying to understand. Oh, here it is. Now you should be able to share.
Let's see. Okay, I think that, yeah, I can share now. Right. Do you see the screen? Can you see the screen?
Thank you. Very well.
Yeah. Okay. Well, so this is a very heterogeneous audience, so it's pretty interesting. I'm gonna talk from a perspective of developing country in the southern global world from South America. And basically, I'm gonna talk about coastal engineering on such coasts which are dominated by tectonics. And I'm gonna touch on issues related with hazards, impacts, and adaptation. So as Professor Pinardi said, I belong to the Ocean Engineering Department here at Universidad de Valparaíso. And we've been working on basically bringing civil engineering to the ocean. I was kind of touched on what you said of this crossroad in the last 20 years between hydraulics, oceanography, and well, coasts, which is something that we've been trying to do here as well. And a little bit of context. So in the Pacific coasts of South America, we're subjected to tsunamis. In the last 15 years, we've had 3 of them, one very large. Earthquakes, every once and then we have large earthquakes. Indeed, we have been affected by the largest earthquake ever recorded by human history in 1960. Yeah, we're also affected by sea level rises elsewhere in the world, and also coastal storms. If we look at wave power maps elsewhere in the world, we find that places like South Africa or Western Australia or South America are the ones that have probably the most energetic waves in the world. But also we have earthquakes because we're in a subduction zone, and in that term, our coast is pretty similar to the Japanese coast, yeah, and also Indonesia, yeah, subduction, well, Alaska as well, yeah. So we cannot decouple issues related with sea level rise with earthquakes and tsunamis. And the idea of this talk is to kind of put together all these type of variables in the decision-making process of design, yeah. Now, just to give you a little bit of context, so If we were focusing in Chile, from the border with Peru to well, the southernmost tip of the country, it's roughly 4,000 to 2,000 kilometers. And if we put the same distance in Europe, would be something about between Gibraltar and Norway. So you could guess that there are lots of changes in terrestrial climate, but also in ocean climate, right? It's a large study site. And if we start looking at the details on South America, so we're going to have the Pacific coast pretty much affected by subduction, and that's why we have the Andes, the Andean mountain range, which is the second highest elsewhere in the world after the Himalayas. But in the other side of the continent is really flat, and we have some of the largest rivers in the world, like the Amazonas, yeah, with large flows and that kind of stuff. Large flows, relatively small velocities. But for example, in central Chile, where my school is sited, we can easily, in less than 200 kilometers, reach the highest mountain in South America, which is the Aconcagua, which is way larger than the highest mountain, for example, in Europe. This is almost 7 kilometers high. So the slopes of our basins or our catchments is pretty high. That means that we have, and the catchments are not that big, so we don't have large flows, large rivers, but they run at impressive speed, yeah, bringing relatively coarse sediments to the coast, and that's why we don't have kind of impressive coasts like the ones that you can find in Brazil, in the other side of the continent. Yeah, really nice white beaches, that kind of stuff. We don't have them. It's a pretty energetic coast, right? And we also have several climates, as I was saying. So if we start from southern Peru towards the south, we're going to have the driest desert in the world, and then we're going to go up to Patagonia. Last week I was in Patagonia, freezing, even though we are in autumn. Yeah, so we have these very large ranges in terrestrial, as I was saying, climate, but in the ocean as well. As we go to Ecuador, as we go north along the Pacific coast of South America, waves become milder, but when we go south, we can have easily significant wave heights of 10 meters on a regular basis during the storm period. Yeah. So this is just to give you an idea on the type of waves we have here. So the distance between central Chile to Japan is roughly 20,000 kilometers, and we all know in this audience that waves can travel and they can evolve, and this is half an hemisphere of the world. So the waves we receive here are they are the largest waves in terms of wave period that you can find elsewhere in the world. Yeah, that means something. There are some other places like Western Australia that also has really long waves. Yeah, but that means something. Long waves, they do have some character, and they are also mingled with locally generated waves, which can be also pretty much energetic, right? So this is the type of thing we can regularly see in the coast. So that's in Spanish, but that used to be my father's office, located pretty close to where I am here in Valparaiso. And after one storm, it was actually a coastal storm. It was actually scoured, so we decided to tear it down. Yeah, unfortunately, he was a kind of victim of this type of hazards, right? But this is the thing. This is the type of phenomena we have to deal every once and then here in Chile. And to do that, sorry, too much noise. In the Valparaiso Bay, we've been using, as well, coastal engineers do, lots of techniques in order to try to understand this very specific test site, which is basically combining, for example, wave forecasts and even projections and of different levels, records, and also cameras, which we process in order to diagnose this patient, which is the Valparaiso Bay. There are several places in the world in which they have some sites which are kind of their own sites, like Cantabria, for example. They're always working with Sardinero and so this is our own, yeah. And we've been working with several tools, like as the one I was just telling you, just to assess the hazard of a particular phenomena. We also can go very deep into calculations such as using CFD in order to compute velocities and hazards and all that stuff. This is just for people which is not in the coastal engineering community. These 2 slides are just to show you what's the battery of tools we have in order to assess any particular coastal engineering problem. Now let's go to, so I'm going to show 2 examples, and then I'm going to start throwing some ideas in between, but 2 pretty applied examples on things we've been doing here lately in Chile. One of them is a rather traditional diagnosis of breakwater, and the other one is using kelp, kelp forests in order to reduce the energy of waves coming from elsewhere in the Pacific. Yeah, so it's kind of both extremes of engineering. So let's start with this one. First, the title is Multiple Hazards. As I was saying, hazards, we have several hazards: coastal storms, earthquakes, and tsunamis, and they are all affecting the same system. Namely, in this case, going to be like a port. Okay, so these are some of the snapshots that were kind of shocking before the area where I went to university. So this was a 1985 earthquake. It was a small earthquake, 7.8 in magnitude. For us, it's small. I mean, we just had last week another one in Myanmar and was similar energy, and it generated large destruction. Well, in Chile, that kind of earthquakes are kind of frequent. We may have them every 10 years, yeah, roughly, like statistically saying, not in the same place because the country's too long, yeah. But these were the impacts of that earthquake in 1985 in the port of San Antonio, yeah. This is the way we reacted. Yeah, if I had to say something to someone that knows nothing about engineering, Chilean engineering, is that we are really good at structural engineering, seismic design of structures, but we're not good at coastal engineering. We were not that good at port engineering, but we've been importing all these ideas of structural engineering to port engineering. And for example, that's just a cross-section in which a new berth site in the same place I showed you just before was built with this seismic design codes, which are now all the time included in new port infrastructure in Chile. Now, we are not good at tsunami engineering. Yeah, we've been learning about this. So this is a photograph of, well, after the 2010 earthquake and tsunami in the south of Chile. This is Talcahuano, and you can see the containers, all of them stuck in the city after the tsunami. And in this particular case, in 2010, I had been working on the design of that particular pier before going to academia. I was a practitioner, engineer practitioner, and I was kind of worried of what had happened with that particular structure with the earthquake and tsunami. Then we visited the site, and the pier was, in perfect conditions. But then we started looking at how the tsunami had affected these areas. And in San Vicente, in this bay, the tsunami was just like a slow increase in water level, whereas in Talcahuano, it was a very impactful and strong current generating lots of damage. So that was kind of a pretty kind of good example on the locality and the local conditions that pretty much affect this type of phenomena, something that we kind of know. I mean, if we're coastal engineers, we know that if we move 200 meters from one side, then the design conditions may change, yeah? But this was kind of shocking, yeah? This is the type of things we saw in this particular site. So, ships on top of beaches, and then 1 year later, in March 11th, 2011, we saw this in Japan, right? And Japan and Chile have had strong bonds in terms of tsunami research and earthquake research since then, and even after the 1960 tsunami, because we have kind of similar settings, right? So this is a video taken here, like a couple of blocks away from my office, and this is Valparaiso Port. It's a really old port. It was never founded, but people started, gathering there in 1536. Which for South American standards is a very old settlement. And now it's the second largest port in Chile. And so when we see this type of structure, we start asking, so what are going to be the consequences within the life cycle of or the remaining life cycle of this port of having a succession of earthquakes, tsunamis, climate change, sea level rise, coastal storms, and so on. So the particular case I'm going to show you is related with this breakwater. This is one of the largest breakwaters, deepest breakwaters in the world. It has in the head 60 meters of depth. I was in Civitavecchia last year in October, and they were building a large breakwater. Also in Genoa, they're building large breakwaters, but this was built 112 years ago. Well, it started 112 years ago, and it took 20 years to build it, right? So it's kind of impressive for the time. It wasn't Chilean engineering, it was British engineering. So I'm going to show you what we've been doing with this structure, which is very important for the port. Sorry for the sound. So this is just one example of the type of interactions you may have in this structure, with, for example, coastal storms. And indeed, there are some, initiation of differential settlements along the structure, and you see some failure modes which are incipient. Probably they are not affecting the entire stability of the structure, but still, it's like an old person that needs to go to the surgeon in order to check what's its condition. So, for example, we can see these type of things. Yeah. Now, I've been working with Professor Taro Arikawa from Japan, Chuo University, and he was he played a significant role after the March 11, 2011 earthquake and tsunami. In Japan, there had been, the Kamaishi, there's a typo there, should say breakwater, it says breakwater, sorry for that, didn't check it. Well, but after this earthquake and tsunami, the Kamaishi breakwater, it wasn't a breakwater, it was a break tsunami. It was aimed to reduce the impact of tsunamis in the town of Kamaishi. It failed because of the tsunami itself. Yeah, there's lots of discussion in Japan if it was effective or not. But the thing is that if you compare the Kamaishi breakwater here in the top and the Valparaiso breakwater, they're kind of similar. Yeah, in Kamaishi breakwater also has 60 meters depth. And then the question is, okay, these people had this earthquake, they invested $650 million in one structure that failed. So what's going to happen with a 112-year-old guy that has been there and will be probably affected by a similar phenomena, which for some reasons that I don't have time to explain is not a fact, but it's very probable. So we've been conducting, for example, LiDAR surveys, all together with multi-beam surveys to have this kind of, millions of points of, the breakwater by combining aerial and submarine surveys. And with that kind of information, we can identify small failure modes, the displacements of blocks, and that kind of stuff, just to have the diagnosis. In combination with, so we've also been conducting, for example, probabilistic tsunami hazard assessments. So what you see in the left is one of 6,000 tsunami models that we've been conducting by combining several possible sources. And they provide basically loads on the structure which we are using in, for example, a three-dimensional model of the breakwater, which actually this was developed by Professor Arikawa in Japan. You can actually calculate the interaction between blocks, which is something which is not that common for structural engineering. Yeah, usually we assume that the elements of a, for example, building, they're connected with nodes and that kind of stuff, but we almost never assume that there can be some sort of displacement between both. So then you have to prescribe the way these elements interact and so on. So this is an ongoing project. The basic idea is to evaluate what's the remaining design life of this structure and what kind of measures should be taken in case we find out that it could basically fail soon, right? Now I'm gonna move a little bit to just show you a little bit more scientific things that we've been doing here. So if we are thinking on earthquakes, these are people that have been working on the 1960 earthquake. So since it was the world most largest event ever recorded by human history, it has been subject to a different, kind of very well-known scientists like Iro Kanamori, who was kind of the founder of modern seismology, and also George Plafker, who actually conducted simultaneous surveys in 1964 after the Alaska tsunami and in 1960. And in a way, he confirmed that there was such an interplate called subduction, which was kind of, it's a long story, but Alfred Behechner proposed this theory of plate tectonics in 1912, and then it was just, dumped away until, this 1960 and 1964 earthquake. And basically, after the contribution of George Plafker, it, raised like a competitive theory, which is nowadays pretty much accepted by the scientific community. So one of the things that it's interesting, at least to me, of this event is that people has focused on the earthquake, but not on the tsunami. There's almost no information on the tsunami. So in 2016, we started working on different avenues to approach the problem. One of the things that it's not directly related with 1960, but it was kind of analyzed in a 2010 earthquake, is that there is a vertical deformation of the coast, which it can be dramatic when we have this type of earthquakes. So if we're thinking, for example, in sea level rise, and sea level rise is expected to be, below 1 meter in 80 years by the end of the century, and then we have an earthquake which moves the crust in the coast by up to 2 meters, or even, you may not even believe this, but in 1960, there was an uplift of 5.2 meters in an island in Chile. Yeah. So how do you deal with that? Yeah. So very different phenomena. Sea level rise is kind of steady, slow, and then you have these sudden changes. So we need to understand what's the cycle of the vertical position of the coastline within earthquakes. And this is the kind of work we've been doing lately. Yeah, we also have been, for example, crossing the boundaries, and this is a work I did along roughly like 5 years, interviewing survivors of the 1960 tsunami, just to try to understand what was the run-up of one particular site. We started looking for run-ups. We ended up capturing stories, like human stories, which were way ahead of a coastal scientist can do. And we've been putting all that information together in order to diagnose this particular tsunami, which is the 1960 tsunami, which, as I told you, wasn't studied thoroughly before. Just one thing. That woman over there is a historian I met while being on sabbatical in this center in Harvard, and she helped me to decode all these interviews we had. So this is just an idea to show you what are the things we're trying to do, and then with numerical modeling, shallow water equations, and that kind of stuff, we can calculate or backtrack. That's a basic idea. Backtrack the source in order to capture those run-ups measured or reported by people. This is a kind of a speculation. We haven't done it thoroughly. Yeah, but anyway, we could basically try, if we are able to do it, to assess which places of the rupture zone may eventually break in the future, right? That's basically assessing the hazard of earthquakes and tsunamis. So I think I'm not sure if I'm running out of time. Shall I go? Okay, yeah, let's go. So let's see some things about the future of our coasts. So these are, sorry for the Spanish, but these are just like the snapshots I'm putting in a book in Spanish. The last 15 years I've been working on generate lots of information in Spanish, because it's not like easy to find, especially for coastal engineers which are not educated in English. So this basically shows 3 types of analysis you can do, like short-term meteorological analysis, climate change, and so on. The things we know is that at least in the South American coast, waves won't change that much during the present century. Yeah, we haven't been focusing on what's the hot topic, which is extreme wave events. Yeah, in a way, we've done some things, but I think we are way behind what's been doing on the forefront of science. But at least we have done some projections of waves, and we know that they won't change that much, right? So, but the thing is that we have climate change, and that's my kid. He's a little bit taller now, yeah. But I'm kind of comparing the sea level rise in central Chile with all these. Well, these are 23 models of the IP of the CMEP5. What is it? Set of data. Yeah. So it's something kind of well known. So the thing is, what do we do with this? I mean, we have data that's telling us projections with a certain level of uncertainty that we know that tells us that the sea level rise will be a little bit higher. So I just wanted to show this video. A couple of years ago, I was in New York, and you've seen this video in several of these several movies. But one of the things that I was kind of interested with this video is that Manhattan was affected by Hurricane Sandy. This is not climate change; it's just one particular event, and then there could be attribution studies to check if it is connected with climate change. But one of the things that I was kind of struck about was that if you go to the promenade here in the Hudson River, you're going to find this type of information. So this type of information, I took the picture from the promenade, pointing upwards, and it was roughly like, well, two pisos, it means a story. It's like 2 blocks, two stories above the river level at that point. And it is saying that basically I guess that with a large level of uncertainty, that could be the water depth by 2015 of a storm with 100 years return period. So that's kind of shocking. And well, New York authorities are showing this to people. So I guess that's a good point, but then you have to take into account. So, well, basically, it's what do you do as a coastal engineer with this type of information, right? We know that something's going to happen. So then we go to coastal adaptation. And this is a kind of an image I adapted from the Corps of Engineers in the US, but I also put some other things here. So basically, these are some of the strategies of adaptation in terms of infrastructure, which could be gray infrastructure, blue, green, brown, whatever, in order to cope with different hazards. One of them could be, for example, sea level rise. But in Chile, as I was telling you, we cannot neglect the presence of other hazards like coastal storms and that kind of stuff. So the thing is, well, so we have this portfolio. And then, yeah, what do we do with this portfolio? We have to study its efficiency, its effectiveness, and so on. So I'm going to show just one example we're doing now. It's on the onset of the research, it's using basically kelp fields. So kelp is a large species, underwater species. And this is a drone taken nearby here in Valparaiso, where you see that the waves start interacting with this kelp field. And the interaction generates turbulence, and we know that's energy dissipation. There's also motion of the waves, which is basically a mechanical energy transfer from the waves to the kelps in order to make them move. And also there's a reduction in the speed within the field, and that promotes sedimentation. So one thing would be to ask, could we use this type of forests, like engineered them and basically try to reduce coastal erosion, which is, I haven't shown things, but we've done several studies here in Chile, and roughly 80% of the beaches are eroding, which is basically they are transferring sand from the exposed area to depths beyond the closure depth. And so this is the type of species we're using. Yeah, it's a long plant, and it grows pretty fast. And for example, here we are developing a prototype, which is kind of borrowed from aquaculture. It contains some structural lines, seedling lines, and here you can see these small individuals which grow pretty fast. And so we've been characterizing this, sorry for the noise, Yeah, we've been characterizing these species, for example, by identifying their geometry, their buoyancy, their structural response to loads, yeah, to basically try to capture what's going to be their interaction with flows. And oh, sorry for that. Too much noise. Sorry for the noise. Yeah. So and here you can see that. So this is our lab. This is where Rodrigo Campos was in charge of this lab. Here you can see waves in the top. Yeah, short waves being pretty much damped by this type of kelps, while long waves, which are the ones that affect us in coastal in Chilean coast, they are basically what is it propagating through the forest. I need 2 more minutes to finish the idea. So we've been using all this pool of models, like for example, Pacific scale wave models, wave watch, propagation models, SWAN, X-Beach, structural models like Aquasim, CFD models, in order to, from one side, actually design a structure that is stable during storm conditions, and from the other side, designing a structure that could be eventually, that's the hypothesis, effective in terms of wave attenuation. Yeah, well, this is the kind of things we've been doing. Yeah, very detailed things, very detailed analysis of flow interaction with individuals, kelp individuals. But also structural analysis of a much larger system. Yeah, so this is kind of a typical pre-feasibility or feasibility studies that you do when you want to deploy something on water. But then we deployed it, and now we are, for example, measuring waves before and after the kelp field, which is growing currently. I don't have videos. Well, I don't have videos of the kelps nowadays, but they've been growing. My group went yesterday to the field. And so this is just a top view of the site where we are growing the kelp, and we hope with this type of formation, which is a combination of cameras and ADCPs and wave buoys and all that stuff, to actually evaluate if the hydraulic efficiency of this kelp could reduce waves in a margin. We are expecting to reduce the wave energy with this this particular prototype in about 10%. It's a small field. It's the size of a football field, but well, we're just trying to guess if it is going to work or not. So I guess that's what I wanted to tell. Last thing is that I put this book, which is called Costas de Chile, which was kind of an effort to put coastal engineering with no equations available to people that are not trained in our field. It's focused on Chilean examples, but you may find also several things which are common for other places, and it's in Spanish, which is something that it's kind of important for us. Okay, that's it.
Patricio, thank you very much. A fascinating set of examples of real problems that you are facing. And I have to say that in addition to the land-sea continuum that we discussed with Achilleas, you bring also the other topic that is very relevant, is the coupling with the tsunami or the earthquake, or the different structural dynamics of your land, which has to be accounted for. And fascinating, yes, the way. So I have a comment which I'd like to tell you about, and that is also I share completely. I love those map projections. Yes, we like it. The world seen finally from the south. That's a very good one. We like it.
Which one?
Yes,
you mean the?
Yeah, it was. Uwe.
This one.
Written that, yes, that's a wonderful one. It's great. Now we have a question here, which I'd like to ask you. Do kelp fields work even in cold southern climatic conditions in Chile? do they also remove significant quantities of CO2 or carbon dioxide from the atmosphere?
Yeah, those are good questions. I think that I could answer the first one. The second one, no, because I'm not a biologist. We're working with biologists anyway. But the kelp fields are, yeah, we can find them in the south, extreme south of Chile. We can also find them in the extreme north. They actually Darwin, Darwin evolution, when he first came to South America, he came through this area. I'm pointing at the southernmost part of the fjords, and he reported kelp fields of roughly up to 70 meters, and it's in his book. Yeah, it's not that the kelps are growing from 70 meters and reaching the surface, because then you don't have light to make them grow, but they can grow at 30 meters, and when they reach the surface, they start, interacting between them, and they form some sort of kind of superficial network. Yeah, so they are there. I was last week with U.S. researchers, and they've been developing quite fascinating research on kelps in California. So it's California and Chile. They are kind of hemispheric twins. We have a similar climate, a little bit similar tectonic setting. We have subduction, though. They have a superficial seismicity, so it's kind of different. But it's spread all through all extreme latitudes, both in South America and North America. As if they sequester CO2, yeah, for sure they do. So the amount, I have no clue. But we've been putting a research project together in order to go along that part, because we think that they can do both. They can do either adaptation and mitigation just by, well, together. What I'm kind of reluctant is that if we think that this type of kelp fields will compete in terms of dissipation with normal structures, then we have to go large. And that brings ecological challenges. We need to understand ecological succession and that kind of stuff that we haven't gone through yet, because we just have this specific site in Maitencillo, next to Valparaiso. Yeah.
Yes, thank you. So we have a Helen from, I guess, from Wales, that is asking about the silos in which you build infrastructures. So the fact that sometimes it is very inefficient, even for funding, she says, for finding a solution to multi-hazards. So how is
can you talk to the microphone, because I don't hear so well? Can you talk to the screen, please, Professora Pinardi? I didn't hear so well, sorry.
Yeah,
sure. That's much better. Yeah,
better now, maybe. Sorry. So let me read the question by Ellen. She has a much better way to say. So I was trying to. Does Chile fund infrastructure projects in a silo way? So I mean,
what is a silo way?
Silo means a separate way, like 4 parts is one thing, for beaches is another, for a certain kind of infrastructure. So like, and also for different hazards. So you can be you finance for like storm surge is your different financing than you have a different financing than it is for tsunamis. Do you have that exploration in Chile?
No. The thing that we have, that we learned from earthquake engineering, is that basically designing for hazards is essentially designing as we used to do, this, but we need to, we usually we incorporate an additional derivative, considering that the hazards could be changing and so on. So it's a change in the way in which you calculate the hazard. Yeah. But sorry, but let me rephrase. If you're thinking that in Chile we are designing, for example, breakwaters like the one in Kamaishi in Japan for tsunamis, we are not doing that. No, we're not doing that. So there's a regular fund from the state going to coastal engineering, and what they are asking for to us, to designers, is basically give the second loop and incorporate the hazard dimension on that design, which means if you're going to design a structure, you have to, for example, have projections of wave and wave extreme conditions in order to shift from the standard kind of stationary approach of design to a design in which you consider uncertainties in the future and also the idea that climate will change. We've been doing that with earthquakes for a while, so we kind of know a little bit about this. The way in which you treat statistics for earthquake and tsunamis is kind of different, and the tools are kind of different. But yeah, so I would say that we are still doing the thing that we've been doing for decades, but with this additional loop in which you incorporate hazards from the kind of climate change perspective. Yeah.
Yes, thank you. I mean, this kelp issue is very relevant also for our school. And, you know, we talk about nature-based solutions, and kelp is clearly a nature-based solution because it is native of your waters, as well as in California, for example. So Uwe is asking, the problem with kelp is that it may not be there when you need. That's an interesting problem. During a storm or tsunami, as it is ripped out, or if it is seasonal, outside the growth season, that's a very relevant problem, I think, because we have the same for seagrass. So what do you say about that?
Yeah, I agree with that. Well, first to say that we are just doing this prototype, we're just testing we're doing a proof of concept to see if it works. Now, the thing is that we have these very variable changes in biomass during the year. And for example, in December, we had these large swells coming from a storm in Northern Pacific, and our prototype ended in the beach. So I'm not sure how much energy dissipated in all that process. Yeah, but well, in theory, it should dissipate something just by being cheered out of the. Yeah, but I agree. It's a big thing. So this is kind of a 2 years project. It's just a proof of concept. If it works, then we're gonna start analyzing survivability. Yeah, the risk of putting this devices there and so on. So yeah, I absolutely agree with the point. Yeah, the thing is that it could be eventually an alternative way of aquaculture as well. So it's not just focused on the idea that we're going to dissipate energy. It could have other uses as well. And if it works, it's basically doing kelp farming in a different way as it's done elsewhere, because we're putting these devices from the bottom and we're kind of testing the prototype.
Yeah, this is very interesting. If I might add, something we are doing in Civitavecchia, by the way, exactly for this reason. We are studying the seagrass. In our case, it's called the Posidonia. That is a maximum 1 meter plant. So it's not something as beautiful and large as kelps. But and in that we find that seasonality is a very important aspect, which Uwe clearly mentioned, and also that has to be accounted for. And also the fact that you need to find out an index of survivability, which is useful for the people who are, going to implement the solution. So, I mean, both relevant questions. Anyway, I just have another one, which I like very much. Is kelp engineering possible in coastal areas having heavy rain discharge?
Oh, that I cannot answer. No idea. No idea.
Sorry,
The
heavy
only thing
river, not rain. Heavy river.
River?
So, river.
I have a river. Well, I have no clue. What's the role of turbidity in the growth of these individuals? So I guess that that's part of the process. I mean, it's interacting with the people from the marine biological point of view discipline, but I have no answer for that. Sorry.
Thank you.
It's a good question. Research question.
It's a good question. Yes, very interesting. So maybe in conclusion, I would like you to give some recommendations to our students and listeners about, the solution way, the possible solutions that are now finally coming out of some real scientific basis. And so maybe I'll ask Achilleas and then Patricio again to give a short conclusive remark.
I'm not sure. Achilleas could start.
Yeah. The perspective as we've seen now, and also Patricio tried to with all these aspects bring into the engineering part, but also collaboration with different sciences, is that my view and understanding when we're talking about coastal resilience is that we need to follow or adopt integrated approaches. So integrated approaches might not mean necessarily that solution will have integrated modeling of different fields or whatever, but these approaches should somehow keep in mind for engineers, for natural scientists, the part where actual proposals and actual research gets into realization, gets into practice. So as an engineer myself, but I've worked in different areas that work with surface dynamics apart from engineering. I see that in our world, at least, if you want something to be funded, to be realized, and to be efficient for the well-being of the community, of the city you're trying to build, the people, the economic activity, you need to always have this in mind. Of course, this needs to have the basis on really solid science, on really solid fundamentals, but a challenge for us scientists is also trying to translate this into non-specialized audience, to convince them that this is the way to move forward, because elsewise or whatever, you'll have to face the impacts. Now that people the last decade or so are seeing the impacts of extreme events, especially those related to climate change, they're beginning to understand this dire future ahead of us. So my main point would be on this: try to do good science, but also try to translate it into something that will pass to society eventually.
Thank you, Achilleas.
Well,
Patricio, please conclude.
I'm not sure if I can say something so wise, because the question is too big. But one of the things that, as a professor here in Chile, one of my main concerns is a very specific, is as Achilleas was saying, is conveying the kind of scientific message to different audiences. One of them is the general audience, which are going to be the users of this solutions. But the other one, which I guess it's very important, is our students themselves. And we are challenged by the fact that the things that we are learning were not taught when we were students, and we are kind of challenged by that. How do we teach something that we were not taught and that we've learned empirically? Yeah, I mean, for example, concepts like risk, uncertainty, IA, and all that stuff. I guess that's challenging from the engineering and faculty point of view. And the other thing I think that's very relevant is that, so I live far away from Europe. We live far away from the US, from where developed countries. But developing countries can also do things according to their own needs and social and economical conditions. it's very easy nowadays to just scroll through the web and find out solutions that could be eventually cheaper and adaptable, and it's the work of coastal engineers to bring those existing solutions into local conditions and check if they are efficient or not. That's one of the things that have been driving me in the last 5 years. And I'm not sure, for example, if solutions in stable coasts like the east coast of the US, adaptations will work here, and that's another challenge. Yeah, we have to answer. Rodrigo Campos should answer this type of things, coming back to, if he comes back, or he stays, whatever. Yeah, but it's like from the global south, we have to be, well, whatever, that's it.
Thank you so much to everybody. We have lots of people still with us after the 2 hours, and very interesting. Thank you to our 2 speakers. Have a good day.
Thank you.
Okay,
Thank you.
Bye.
Bye.
goodbye.